hear Federico Echenique from the California Institute of Technology talking about Savage.
It's a paper with it's a paper with my colleague Kota Saito. It's a paper about the relationship between a model and behavior or data, maybe like most papers are. But this paper is about the model that this paper is about subjective expected utility, which is what SEU means, and the behavior is behavior in the market. So Savage characterized expected utility or subjective expected utility when the behavior was a preference relation. So he imagined that you could observe every possible comparison that you can make between each possible state contingent alternative, and then he characterized the behaviors in the sense that are compatible with expected utility. So we are going to do the same, but instead of having the data that Savage has, we're going to have market data. So this is the kind of exercise that we're going to do. It's going to be about maximizing utility, yes, subject to a budget constraint. So, so this is the model, okay? Very familiar model. So P is price, I is income, X is consumption vectors, and consumption will be state contingent consumption. So the S there is a set of states. Okay, so you're maximizing utility subject to a budget constraint, and what you're buying are state contingent payoffs. Okay, it's a very maybe the most basic model of all. And behavior will be like this. Closer. Can you hear me now? Yes. So behavior will be like this. It will be about observing a chosen consumption bundle at some prices and some income. Right? So suppose that you see this. So you see purchases X1 at the budget, at the first budget, and you see purchases X2 at the second budget. And we know that this is not consistent with utility maximization. So if you have this model and you observe these choices, then you know that you have refuted the model. Yes? Because if you buy X1 when you could have purchased X2, and you buy X2 when you could have purchased X1, then you can't be maximizing utility. So more general, the answer to the question when is observable behavior consistent with utility maximization is when the strong axiom of rate preference is satisfied. So this is a violation of the weak axiom of rate preference, and the strong axiom is equivalent to the weak axiom when you have two goods. So this is a good example of what can go wrong. Okay? So this is an old question and old answer. So what's new? What are we doing in this paper? Well, we're also going to look at utility maximization, but we're going to ask that utility takes this form. So we're going to ask that you're maximizing utility function, but this utility function has to be of the expected utility form. So the function U has to be strictly increasing and concave. So we're going to restrict attention to the case of risk aversion. So the utility function has to be concave. And mu is a subjective prior. Yes. So this is the model. The model is a model of expected utility with risk aversion. You're buying a state contingent bundle X subject to a budget constraint to maximize expected utility with risk aversion. So it's as conventional model as you can imagine. Okay. So right, and you know, I will tell you what you know and what you don't know. Okay. So this is the model. So here's what you know. So you're given behavior, which is that you're given data on purchases of state contingent monetary payoffs in a setting of complete markets, so complete ROW markets. Okay, so this is what you observe. You observe bundles, prices, and income. You observe purchases on these bundles. And what you want to know is when is the very conventional model of expected utility with risk aversion consistent with this kind of behavior. So you don't know the agent's utility functions, and you don't know the probabilities that they assign to the different states. All those things are in the minds of the agent, or we think that the agents behave as if those things were in their minds. And what you do observe is you do observe the purchases. of state contingent payments. Okay? The question is, when is observable behavior consistent with subjective expected utility maximization? And the answer will be when Sarsia, which is our name for the strengthening of the strong axiom of real preference that captures this case, is satisfied. Okay? So we're going to solve the problem of Samuelson or Afriat or whatever your favorite economists who have worked on these things, for the particular case in which utility function has to take the form of expected utility. Okay, that's the nature of the exercise. So I will give you a warm-up first. So the warm-up is a 2x2 case. 2x2 means 2 states and 2. It doesn't mean 4. It means 2 states and 2 observations. Okay. So if you think about the 2 states case, the model is like this. You're maximizing mu1 u of x1 plus mu2 u of x2. So this is the expected utility from consumption x1 in state 1 and x2 in state 2. There are 2 states. Subject to a budget constraint. So you buy ROW securities for the states x1 and x2, and this is your budget constraint. Okay, so this is your model. You don't observe utility and you don't observe the prior, but you do observe choice at different budgets. Okay? And I want to know when are the choice at different budgets consistent with this model. So can you, what do you think? Is this consistent with the model? Well, this is inconsistent with utility maximization. So in particular, it cannot be consistent with the maximization of expected utility. So of course, this is inconsistent with the model. Okay? The model maximizes some utility, so of course it has to, whatever the data is, it has to satisfy warp or SARP, right? So the question is, what else? What else does the model require? So look at this data. You buy X1 at the first budget, and you buy X2 at the second budget. Yeah, let me see if I can pull a Mick Jagger. So I like to move around. Okay, so you buy X1 at this budget, and you buy X2 at this budget. And the question is if this is consistent with utility maximization. Maximization of subjective expected utility. And so this is, first of all, consistent with warp. This is not a violation of warp. So it's not a violation of SARP, because I have 2 goods. And therefore, this data is consistent with the maximization of some utility function. Okay? So that's fine. So these data are rational. They're rationalizable with some utility function. However, they are not consistent with the maximization of expected utility. And the way in which you can see that is in the following. So suppose that it were. Okay? So suppose that this data is consistent with the maximization of utility. Okay? Subject to, with risk aversion. Well, if that were the case, then consider the green budget. Okay? How did I come up with a green budget? I took the same prices as these, and then I gave the consumer extra income so that the budget line would pass through X2. Now, if the consumer is maximizing subjective expected utility function with a concave utility, what would the choices be on the green line? Well, if you think about it for a little bit, you realize that demand is normal in this case. So you have to buy more. You have to buy a bigger bundle. And you can see that by looking at the marginal rate of substitution. So the marginal rate of substitution in this case is probability times marginal utility divided by the probability of the other state times marginal utility of the other state. So on the green line, I have to buy more of at least one good, but the prices are the same. So MRS must be the same. So you can't buy more of one good and less of the other. Okay? So you have to buy more of both goods. So therefore, you must buy something here on the green line. But if you buy something here on the green line, then you do violate warp. Okay? So this is this data is not consistent with the model. In fact, it's not consistent with normal demand, with normal rational demand, which is one implication of the model. Okay? So this is a very basic implication of the model. Okay, very good. So we found one way of strengthening warp that is necessary for the data to be consistent with with the maximization of subjective expected utility. Okay? What else is there? Well, I'll do one more. Okay, this one will be the last one. Consider this data set. So you buy X2 out of this budget, you buy X1 out of this budget. And now I have put in the 45-degree line here. The 45-degree line is the line at which you are fully insured. Okay, you consume the same in both states. So X2 is on one side of the 45-degree line, X1 is on the other side. Now, this is also consistent with warp, so it is consistent with the maximization of some utility function. However, it's not consistent with the maximization of expected utility. And you can see that as follows. So suppose it were consistent. So if these choices were made by a consumer that maximizes expected utility, then I can go and I can look at the indifference curve through X1. So that's the red curve over there. So the indifference curve has a property that if you look at anywhere on the indifference curve and look at the tangent of the indifference curve, then I get the marginal substitution. Right? This is what the marginal substitution is. So what I can do is I can walk on this red indifference curve until I get to the 45-degree line. And on the 45-degree line, if you look at MRS, because I have full insurance, I can read off the ratio of the priors at the 45-degree line. So if I look at the tangent of the indifference curve at the 45-degree line, I know that this tangent here will be identified by the priors, by the ratio of the priors, mu S1 over mu S2. So this picture tells me that whatever the ratio of the priors is, it is such that the tangent is flatter than these prices. So since X1 lies on this side of the 45-degree line, I know that this tangent must be flatter than these prices. And now you see what the problem is. Because if I repeat the argument from X2, I find that the tangent here has to be steeper than these prices. But these prices are steeper than these prices. And these prices are steeper than this tangent. But this tangent must all be parallel, must all be the same, because it's a unique prior. So this data set is also inconsistent with expected utility maximization. So that these two cases, it turns out, exhaust all the implications. So you need to rule out this, and you need to rule out this. And that's necessary and sufficient for rationalization by expected utility function. And I will be more formal about what exactly that means. Okay, and I will go back to these pictures later. They end up being very useful to thinking about various things. Okay, that's the end of the warm-up. My co-author is super worried that people will think that 2x2 state is all we do in the paper. So I put in a lot. I have to be very clear about it. Okay, so the main theory of the paper is that data set is rationalizable by subjective expected utility if and only if it satisfies this axiom that I will show you later. Okay. Let me advertise another paper that I presented. If you were in Sao Paulo, you might have seen it there. It turns out that the problem in this paper is mathematically very similar to the problem in the paper I presented today, but it has to do with discounting utility. Okay, so we have in this other paper we have a characterization for discounting, also very classical model, discounting utility with a concave utility over money, and also quasi-hyperbolic discounting. And in that paper is has an empirical application as well to some data we took from an experimental paper. Anyway, so let me talk about the model. So like I said, the model is really super conventional. There's a finite set of states. the state contingent monetary payoffs, we call them monetary acts. The price vectors are never negative or never zero, but these are prices for out of the blue securities for these states. And yeah, and that's it. What is a data set? A data set is a finite collection of purchases. So you buy a monetary act at a given price vector, yes, and you see finitely many choices of this kind. So this is exactly the same kind of data that you have in standard level preference exercises. Okay. A little bit more notation that I'm going to need. So delta S, the simplex, is the set of probability measures. And we don't consider the case in which some state has probability 0 because that state would be empirically irrelevant. So we don't need to think about that. Okay. So this is the set of all the strictly positive probability measures on S. Script C is a set of all the strictly increasing and concave functions. So I'm going to be looking for a rationalization with a utility function that is strictly increasing and concave. So everything here is about the risk-averse case. I have nothing to say about the case where which doesn't satisfy risk aversion. And B is the budget. So BPI is the set of all the bundles of state contingent consumption you can afford at prices P and income I. Okay, very good. So this is the model. The model is maximizing expected utility subject to a budget constraint. Yes. And a data set is consistent with the model if the following is true. So I have a data set of finitely many purchases, consumption bundles subject to price, and I will say it is rationalizable or SEU rational if there exists a prior mu, and if there exists a utility function over money C, such that for everything that's affordable at prices P and the income that I used when I purchased XK doesn't give me more utility. Yes? So this is the standard notion of rationalization, but where I have adapted it to the model that I have here, the model of expected utility. All right? So the exercise is, which data sets are consistent with, which data set are SEU rational? That's the question that we address. Okay? Let me very quickly mention the existing literature. So this type of problems has been studied before. There are papers from the 80s, late 70s and 80s, most notably a couple of papers by Halvarian and a paper by Green and Srivastava. And there's a very recent paper published last year by Kubler, Seder, and Wei, which all deal with a case in which mu is objective and observable. So the prior is part. This is about objective expected utility. So the prior is part of the data. And I can tell you a bit more later about what exactly these papers do, but sort of the final solution to the observable case is given by this paper. It's a very nice paper, which works with, and I can tell you later how it relates to our. But they are dealing with a simpler problem because the probabilities are given as part of the data. In our case, it's subjective. Okay, so let me. So what I'm going to do is I've been promising this axiom, right? The version of the strong axiom real preference that works for subjective expected utility. So what I'm going to do is I'm going to derive the axiom. Okay, I'm going to calculate it and essentially show you that the axiom is necessary. And I will do that. I'll do it first in a special case, and then I'll do it in general. So you can see from the special case how it works. Okay, so the special case is suppose I have only one observation. And suppose that the probabilities are objective and known. So I know the probability. Okay? And let's suppose you use differentiable. It doesn't really matter. Yeah, this is a good idea. No. Okay, thanks. I'm going to break a cup. Suppose mu is differentiable. So I can look at marginal substitution, but But remember, U is concave. So, even though in the result we not assume it's differentiable, I'm not too far away from this case. Okay, very good. So in this case, the model looks like this. So I'm maximizing expected utility subject to a budget constraint. And the first order condition looks like this. Okay? Now, think about what I know and what I don't know. So now I am analyzing the case in which I do know the probabilities. Okay? So I know mu, and I know p, and I know x. I don't know u prime, and I don't know lambda. Very good? So here's what I can do. I can divide price by the prior, and this gives me something you could call risk-neutral prices. Okay, it doesn't matter. You can call it that if you want. So then what I have is, it turns out much simpler, because I have marginal utility has got to be equal to lambda times something I observe, okay? Risk-neutral price. So the model means that I'm equating marginal utility to the Lagrange multiplier times price. And I have only one observation. So this model you know how to deal with, because if you have done some problem sets, you know that when you have something like this, you divide one first order condition by another, so you get rid of the Lagrange multiplier, and then you have on the left the ratio of marginal utilities, and on the right you have the ratio of prices, and you observe the guy on the right, you observe this and you observe this, and now you know what the implications of the models are. The implications are like this. If this guy is greater than this guy, then this ratio must be smaller than 1 because of concavity. So you know that this price ratio has to be smaller than 1. And if you want, you can call that downward sloping demand. Okay, so the implications of this model are downward sloping demand. If this quantity is greater than this quantity, then the ratio of prices has to be smaller than 1. Okay? And this exhausts the implication of this model. So if this is satisfied, then you can construct a marginal utility from the prices, and that marginal utility, if you integrate it, you will have utility that explains the data. So it's a very, very simple integrability exercise. Okay, very good. What happens in general? So let me try to do the same thing, but in general, when I have k can be any number of observations, and when I do not observe mu. So I start from the same place. I start from the first order condition, but now I don't know mu. And I'm going to have more than one observations. Okay, so let me take the first step just like before. I divide one first order condition by another. And now I have my observations, x, kx, x, k prime, s prime, and the Lagrange multiplier is different from every observation. Right? So now it's not quite so easy, because now I observe the ratio of prices, and I observe the quantities, but these guys, I don't observe them. So I need to deal with the effect of the ratio of probabilities, which I do not observe. And now I have different Lagrange multipliers for different observations, so I can't just cancel out the Lagrange multipliers. So what am I going to do? I'm going to base everything on the idea of downward sloping demand, just like before. So I'm going to look at pairs of quantities, one greater than the other, which will allow me to say that the ratio of marginal utility is smaller than 1. And I'm going to try to say something about prices, about the ratio of prices. But of course, these nuisance terms here, they can screw up. I can't say anything because I don't know what they are. So I'm going to pick the quantities in a special way so that these guys cancel out. Let me show you an example about how you can do that. So here's an example. So I pick 3 pairs. This guy greater than this guy greater than this guy, and this guy greater than this guy. So how do I pick them? I pick them in such a way that the stuff I don't observe will cancel out. So what do I need to do? To get the lambdas to cancel out with each other, I need to have each k on the numerator exactly as many times as it's in the denominator. and each state on the numerator exactly as many times as in the denominator. So think about, look how I did it here. So I have K1 on the left, but also K1 on the right. I have S1 on the left, and then also S1 on the right. So then when I take the product of these ratios of marginal utilities, then on the right-hand side, the lambdas cancel out with each other, and the mu cancel out with each other. And I'm only left with prices. And I can reason exactly as I did when I was only talking about downward sloping demand. In a sense, I am imposing that the downward sloping demand property holds, but I'm imposing it only in particular situations, in those particular situations in which I can cancel out the effect of the stuff I don't observe. Okay? And this turns out to be exactly the content of the theory. The content of the theory will be, if you want, downward sloping demand, but qualified, so that I only impose it in certain situations and not in others. So the concavity of U tells me that this ratio has to be smaller than 1. Why? Well, because I picked this guy greater than this guy, so this is smaller than 1. This guy greater than this guy, so this is smaller than 1. This guy greater than this one, so this is smaller than 1. So the product of terms that is smaller than 1 is smaller than 1, and therefore this must be smaller than 1. All right? So that's the axiom. So the strong axiom, so we're trying to make it sound like SARP here. So the strong axiom of revealed subjective expected utility theory, expected utility, is that for any collection of pairs in which the guy on the left is always greater than the guy on the right, every state appears on the left as many times as on the right, every k appears on the left exactly as many times on the right, the product of the ratio of prices must be smaller than 1. Okay? And so the theorem says that a data set is subjective expected utility rational if and only if it satisfies Sarso. So the calculation I did is essentially the proof of necessity. Yes, it doesn't it doesn't evolve much more than what I did. I guess you need to take care of the fact that you may not have differentiability, but because you use concave, that's simple to do. The main work lies in proving sufficiency. So the axiom, at least to me, seems in some sense relatively weak. But it turns out that you can prove that it is sufficient. And the way in which you do it is that you set up, basically, you set up the system of, and this is, by the way, also the way in which the results of Varian and Green and Srivastava work. You set up the first order conditions as a system of inequalities. Now, in their case, this system of inequalities were linear because the probabilities were observed. But in our case, they're not linear because we don't observe the probabilities. So that's the main difference between the two approaches. And then you also have some inequalities to capture concavity. And then basically you prove from the right version of duality that there is no solution to the system of equations if and only if the axiom is satisfied. That's kind of where the work in the paper lies. So let me go back to the 2x2 case because I think there are some interesting comments to make once you know the result. So in the 2x2 case, this is what it looks like if you string together these first order conditions. So it looks like this. So what have I done here? I have taken K1 up here and K1 up there, so the lambda K1 will cancel out. K2 and K2, so lambda K2 will cancel out. S1 and S1, so the mu for S1 will cancel out, and S2, S2, so mu for S2 will cancel out. So, okay, so now I have this equation, and this is the, this is what I want. This is what I can say some definitive because I can say when some quantity is greater than another, how it is related to price. Okay? Now, so there are two cases in which I can say something. Now, so this is the first case, the case when this guy is greater than this guy and this guy is greater than this guy. So what does that mean? Well, it means that for every K1, sorry, for K1, this is greater than this. And for K2, this is greater than this. Okay? That's this. I'm saying that this is more than 1 and that this is more than 1. Okay? If you think about it, each one of these two cases will correspond to the two pictures I showed you in the beginning. But I'll go back and I'll show you the pictures. So you need to remember the pictures. Anyway, the other case is in which for S1, the quantity in K1 is greater than the quantity in K2. And for S2, the quantity K2 is greater than the quantity K1. That's this case, where this guy is greater than this guy, and this is this. So this fraction is more than 1, and this fraction is more than 1. Okay? So you can either go down, or you can cross it. But either way, the product on the left will be smaller than 1, therefore the product on the right will be smaller than 1. Okay? So both of these are sort of downward sloping demand type of properties. So let me first consider this one. Okay, that's this picture. It's when for S1 the quantity in K1 is greater than the quantity in K2, and for S2 the quantity in K2 is greater than the quantity in K1. That's this case here. Okay, if you label the axis correctly, but it doesn't really matter. Okay. So the 2x2 case is captured by these two cases. And each of the two cases has something to say about some qualitative feature of the theory of expected utility. So in this case, if you look at these quantities, you see that the ratio of prices must be smaller than 1. However, I drew the pictures in such a way that you get a violation of the axioms. So if you take the product of the prices, you get something greater than 1. They go in the wrong direction. Okay? Now, here's what I want you to notice. This greater than this means this comparison and then this comparison. In each case, the state is the same. So if I look at a weaker model, not expected utility, but a weaker model of state-dependent utility, it will have exactly the same implication. So if I allow the utility to depend on the state, since I am comparing for the same state, this way. Since I am comparing from the same state the ratio of marginal utilities, this will also be smaller than 1. And this will also be smaller than 1. Therefore, state contingent utility, which is a model which has no place for a prior. Okay, the prior has no meaning in the state contingent model, has exactly the same implications. So remember the axiom. The axiom says that any sequence that has some properties must satisfy this. If I strengthen the second one to be that the state on the left is the same as the state on the right, then this axiom turns out to characterize the strong axiom revealed state-dependent utility. So expected utility is captured by our version of the strong axiom preference, Strausz. But expected utility is a particular case of additive separability. And additive separability is state-dependent utility. Yes? It's a particular case which is very important because it has a place for a prior. Now, if I weaken the axiom by strengthening the sequences for which I impose the downward sloping demand property, and I weaken it in this particular way, the model I'm capturing is a state-dependent utility model. So the model are obviously nested. I know that, right? But this is exactly how the axioms are nested, how the relevant real preference axioms are nested. They are nested by the difference in how I require the states, how I am accounting for the state. The source of that is simply this, that it's enough to do this state by state. And I don't remember if I have, no. But so anyway, so there's a theorem in the paper that says that this axiom is necessary and sufficient for rationalizability with a state-dependent utility. Now, that's all very good. What I would like to be able to show, sorry, I should show you one more thing. So if you like your axioms, your real preference axiom to have a cyclical syntax, then you can write that axiom in this way. So it rules out certain cycles. So if you think that for aesthetical reasons that's better, you can do that. Unfortunately, you cannot do that with the reaction for expected utility because the reaction for expected utility involves essentially two simultaneous cycles. So you can't write it as one cycle. Okay. So qualitatively, the theory of expected utility has, in some sense, two components. The first is to require additive separability or state-dependent utility. And the second one is to require that you have to be able to separate the utility of consuming XS in state S into the probability of state S and then the utility of consuming state-independent utility. So the second step of teasing out the probability is, of course, a very important step in showing that, in talking about the content of expected utility theory. Now, how exactly do you do that in this context? It turns out to be much more difficult than in the Savage or the Anscombe-Bowman framework. To separate out the utility, that step from state-dependent utility, that step turns out to be very delicate. I can do one thing based on just adapting the idea that I used for state-dependent, and that is the following. So remember my second case, where you had consumption on one side of the diagonal and consumption on the other side of the diagonal. That's when I look at utilities like this, okay? Observation K1, you consume more in state 1 than in state 2, but in observation K2, you consume more in state 2 than in state 1. That's when I'm looking at this product times this product. And here the prices are wrong. That's why I have a violation of the axiom. Okay? The prices should be smaller than 1, but they are not. Okay? So what can I do? Well, since I'm comparing within the same K here, I can make U be K dependent. So I can use a different utility index for each different observation. But the prior will be the same. Okay? So what I can do if I write down the right axiom, which I didn't bother to do, but if I can write down the relevant axiom for this, is characterize a model in which you have a prior. The prior is stable and the same across all the observations, mu. But you use a different utility index in each different observation. That's what I can say. Now, this model, I'm going to do 5 minutes? 5? Okay. So let me use the time I have to talk about this. So the only previous paper which has results with subjective probabilities, with non-observable probabilities, is a paper by Epstein. And here's what Epstein does, and I can tell you the relationship with our result. So Epstein was interested in exactly our setup. So you have real preference data, you have data on state contingent purchases at different prices. And he wants to know when the data are consistent with the model of probabilistic sophistication. So what is that model? The model of probabilistic sophistication is much weaker than the model of expected utility. It's a model in which what you care about is so you have a prior over state, and every time you buy a state contingent bundle, it implies a probability distribution over monetary payments. So you have prior mu, and you buy X. Then, in a sense, the composition of mu with S gives you a distribution over real numbers, which is a distribution over monetary payments. So the model of probabilistic sophistication says that the agent has a utility function or a preference relation defined over distributions over monetary payments. Okay? So it involves a prior, but it doesn't need to take the form of expected utility. So here's what he said. He said, suppose that you have two observations. So you buy X at prices P, and you buy X prime at prices P prime. And suppose that, in observation P, consumption in state 1 is more expensive than consumption in state 2. However, you buy more of state 1 consumption than state 2 consumption. How is that possible? How can you buy more when something is more expensive? Well, it has to be that you think state 1 is more likely. And on the other hand, suppose that, in observation prime, consumption in state 2 is more expensive than in state 1. And nevertheless, you buy more of state 2 consumption. And further, suppose that one of these two inequalities are strict. Well, then there's a contradiction, right? So Epstein shows that this is necessary for probabilistic sophistication. He doesn't know if it's sufficient, and we don't think it's sufficient, but we don't know. We don't know the. We don't have a characterization for this model. However, if you think about it, this looks exactly like my second figure, right? One observation is on one side of the diagonal, the other observation is on the other side of the diagonal, and the price ratios are wrong. So the second figure, the one in which I know that is related to the existence of a stable prior across observation, that figure is also the one that is capturing Epstein's necessary condition for probabilistic sophistication. So it's one step in the right direction. So if you wanted to, if you have expected utility theory, you want to decompose it into one part having to do with a prior and another part having to do with state-dependent utility or additive separability, then the additive separability part is pretty satisfactory. The other part is the one in which we don't have a very good way of talking about it, but it has got to do with these ideas. It's got something to do with these ideas. Since I don't have time, let me just show you this because it's beautiful. So one question we got, which was a bit more like a dare than a question, but it was, can you come up with a data set of risk-averse, probability sophisticated agent that nevertheless violate our axiom? And so here's the example. So this is the data set, okay? So the data set is one observation you buy here, you insure at these prices, and then you buy this over here at these prices. This is a violation of our axiom. Notice, it violates the state-dependent part. It doesn't violate the second part, which is good, right? Because I think that probability sophistication has something to do with the second part, okay? So this is a violation of the state, the additive separability part of the axiom. So here are my preferences that give rise to this that can rationalize this data set and which are probabilistically sophisticated. So I'm going to be probabilistically sophisticated, which means I must have a prior of a state. And the prior will be uniform, okay? Probability 1/2 each state. 2 states, 50-50, okay? Now, I'm going to construct the utility function over CDFs of money, over probability distribution over money, by giving you a utility function over x's. And this will be convex preferences, which make sure that I'm risk averse. Okay, and here they are. They look like this. You see what's going on? So it starts out, oops, very convex, but it becomes more and more risk neutral, and then it's fully risk neutral. Okay, you can write down this utility function if you solve enough quadratic equations. You can write down utility function for this. So it looks like this. This is the indifference map corresponding to this. And if I superimpose it with the data, you see that, sure enough, at these prices, you want to buy this guy, and at these prices, you want to buy this guy. Okay. And you can make it strictly convex also if you wanted to. That's not hard. Okay. Yeah, so since I don't have time, let me just give you an overview of the different. So the paper has a couple of different things. So often people ask us, okay, so this is a theoretical exercise, but a lot, many of the the main reason why people are interested in real preferences is because they can actually take it to data. I don't know if that's true, if that's the main reason people are interested or not, but so in the paper we have a discussion of the possible data you can use. There are some experimental data which look exactly like this, and arguably you can do something with field data as well. I told you about probabilistic sophisticated agents. You can use the axiom to compare expected utility with other models, and that's in fact one of the main uses of the axiom. Is you can use it to see, if models that look different, that have a different formulation, are in fact behaviorally different. So the max-min model is an obvious thing to think about. In the 2x2 case, max-min is not different from expected utility. So any data set that is max-min rationalizable is in fact also rationalizable as expected utility. However, that's only a feature of the 2x2 case. So with more observations and or with more states, there are data sets which are max-min rationalizable but are not expected utility rationalizable. So that's all that is in the paper. I told you before about the relationship, the literature on objective expected utility. So the axiom, the way Kubler and co-authors wrote down their axiom, the syntax is a little bit different from ours, but you can show that there's an equivalent formulation of the axiom that has exactly the same kind of syntax, and you can see the relationship between the two things, and that's also done in the paper. Finally, you might wonder, okay, so how is this different from Savage? If you try to formally answer that question, you need to compare the framework in Savage to our framework, and it's a bit it's a bit artificial. But what we did is that we looked at the real preference relation. So Savage's axioms are axioms on preference relations. So the candidate preference relation from our data is the real preference relation, which is X is real preferred to Y if you bought X when you could have afforded Y. So that's obviously a very incomplete relationship. So there's no sense in which it can satisfy axioms like completeness. So the first axiom of Savage is that the preference is a weak order. So of course it can't satisfy that. But if you rule out the axioms that the whole setup or rules out that just can't be satisfied because of the nature of the exercise, then it turns out that we can prove that our axioms imply all remaining of Savage's axioms. So if you're a decision theorists, they know these axioms by heart. So if you tell them, okay, so tell me P5, and they will tell you P5. So if there are any decision theorists in the audience, yeah. I mean that if you take Savage's axioms as a logical statement about a preference relation, then the following it is true. If a data set violates P2, P4, or P7, then it violates our axiom. and no data set can ever violate P3 or P5. That's what, and by that I mean that the preference relation that we use is the real preference relation, and also that the violation isn't due to incompleteness. So the violation is because the preference goes against what Savage's axiom says. And so if you remember this, well, these are good for you. Otherwise, it was only 20 seconds. Yeah, I won't. I'll stop.
Okay, let me start by apologizing for this should be all discussants here should be young, smart junior faculty, and in my case, they got wrong in all dimensions. But and the second thing I want to apologize for.
Well, you're tall at least.
Yeah, that's true. The other thing I want to apologize for is like usually you would expect me to simplify the presentation, but I think it's impossible. Federico did such a great job here in making it very simple that I cannot do better. So I'm going to complicate things instead. So let me explain the part that he didn't explain. So if you look at the title, this is where Savage shows and this is where market goes. So basically, you have an axiomatic characterization of Savage, and this potentially should be applied to market data. So that's the explanation for the title of the paper. So if anything, that's my contribution. So what I'm going to do here is like, I'm going to think about the way like textbooks are compare classical approach to revealed preferences. So when you think about consumer choice, you usually present in two ways. First, we can use this, what we call the classical approach, which we define a set X. Let's think about bundles in general. Preferences defined on those sets. And then those B's are the budget sets that we'll show in our theory. And then we make assumptions on preferences, and then we have a behavioral assumption I'm going to be talking about. And from that, we derive choice functions. The revealed preferences approach, we start with the set X, let's say the bundles. We then define the budget sets and choice functions that map, like for each budget set, defines how you choose among the items in those budget sets. And then we make directly assumptions on those choice sets. Let me be more precise. We usually assume rational preferences like a pre-order in those sets. And the behavioral assumption that we assume is that people always choose the best of the feasible goods there, so the best in their budget sets. And then this induces a choice function, which I'm going to denote this. This is basically the thing that is in Mascolay, so there's nothing new here. And then for the revealed preference, we take the weak axiom, and the weak axiom says that if you chose X when Y was available, then next time, if you choose Y, then X must be also among your choices when you possible choices when you if X also belongs to the budget set. Now, given the weak axiom, this induces a preference, induces a preference relation, which is the revealed preference relation on the choice on X. And in which case was so the question we make to connect the two things is that first, in one direction, is whether the choice function induced by the rational relation satisfies the weak axiom, and on the other direction, whether choices that are satisfies the weak axiom rationalize can be rationalizable by some preference relation. Okay. So what I want to think about is really the sets X and the budget sets B, and beyond that, I want to think about this sets with M call A, which are the potentially observed choice sets. This is what are the really data sets that we can really have access to, okay? And this is related to another nice paper by Federico, which is coming out in AER, which is the idea of what is empirically really relevant here, or what has empirical content here. So once again, classroom, what is X? Apples and bananas, like sets of bundles of apples and bananas. What are B's? Those are like basically Walrasian budget sets. And what is A? Well, I'm going to be interested here in the cardinality of these sets. And it's usually, you can think of what is feasible. You can have like a finite number of observations of those budget sets, or those choices made in those budget sets. So then in this case, we can again relate. So just to see how important this is, like when we stick to this finite number of budget sets, and for Walrasian budget sets, then the weak axiom is no longer equivalent to rational preferences, but you need to add the strong axiom to get transitivity. So this shows the importance of the feasible budget sets to connect the two, to the observable sets to connect the two things, right? Again, but the nice thing about the apples and bananas example is that we have a finite set, we have a Walrasian budget set, so we get everything that we want, like the theory has empirical content. But it's a little bit too little ambitious, in the sense that that's not what all that we want to understand. We want to understand how people choose, like between, whether they consume now or later, in which state of nature, whether a bunch of things that involve both the time and uncertainty dimensions. So let's do arrow the brew. Let's add index apples and bananas by time and states of nature. Now, those budget sets are large and possibly very complex, depending on whether, like we have, for instance, incomplete markets and things like that. The bad thing is now the cardinality of the set is only one, because we only see the guy make, if we think about this, there's only one choice that you make, right? So basically, how can you, cannot test the theory, like if we don't add other, like other axioms, or if we don't restrict preferences somehow, for instance, assuming separability or things like that. So we need to add more structure than simple rationality. So let me get back to the paper. So the paper does the same thing with Savage, right? So once again, now we have, well, like states, outcomes in our, the X now is like mapping from states to outcomes, and okay, and okay, I'm sorry, and we want to understand what are those budget sets here, and what are the observations that we have from the data. So let me go to the paper. So the paper, if you think about the basic definition of the paper, of the subjective expected utility rational data set, it gives us everything, in the sense that we here we understand what is our set X. So we have our states are just basically static states, in the sense that they're like one-shot choices, and the outcomes are contingent consumptions. X are contingent consumptions. We have complete markets. So essentially, we're back to apples and bananas, and that's, I think that's what Federico showed us. In fact, like he started everything with revealed preferences and showed us, remind us of what revealed preferences is, because really the model, like the way we thought about the problems that was really one that where you can apply basic revealed preference and strengthen it to test like a more sophisticated or a more specified theory, right? The question is, if you want to apply really this for market data, is it reasonable to do that? And the reason why I think about that, I'm sorry for the lame figure, but basically, I think the way I think is like, I'm sorry, choices like here should be somehow, different from choices here in the sense that you should anticipate what's going on in the as we move in the tree, and we're treating basically what we're doing is we're treating all those things identically. This seems like what we do in lab experiments, and that's. But if we really want to take the part of market in the title seriously, I don't know how reasonable is that to think about that this is a good choice of environment. So what can we do about it? Should we sophisticate the model and impose more structure? I really don't know, but maybe there's a compromise, something that we could do to keep the model track. So the rest of the things I was going to do is like to help get an intuition, but I'm sorry, I cannot do as well as Federico did. So let me just skip to some. I think I have all the colorings as well. That trying to be intuitive, but I mean we've seen all that. So let me do something else. Let me just ask some questions that I think are may help. Some of them that I had to do, Federico already explained here. So, but basically, when I think about, for instance, pure separability, what we think about is like let me assume that the guy chooses the same thing twice in two states of the world. In this case, I think about 3 states of the world. But the only difference between one choice and the other is that in one of the cases, the guy chooses a different quantity of the third good. So the interesting thing here is that because of separability, this should still hold, right? And of course, the axioms should imply this kind of things, right? What I would like to say is like how we get from the axioms to this thing, to this relationship that the marginal rate of substitution between two goods should not be affected by the choice of the other one. This is just this is more like the kind of things that not there or not in the paper, but those are good examples to show the theory in action. So, this is another of the. This is exactly his example of the 45-degree lines. And this is comparing the extra requirements. So basically, I guess if I had asked for the slides, I would have saved a lot of time. So the other thing is those two are the things that you answered here, which are also first. What we know, like Federico commented this twice here, I think, that when we have only 2 goods, the strong axiom adds nothing to the weak axiom. So the question is, does more observations add anything to 2 observations? The case of Strausz. And the other thing Federico already did show an example, but I think that's one thing that the example we gave here is very nice, and I would like to see in the paper how the 2 ratios in the cross thing. It's interesting to see how strong axiom leads to the two assumptions in the 2 by 2 case. To wrap up, I think the only thing I'm concerned about is like really how natural is the choice of the set X in the case of subjective expected utility. And the other thing that I would like to know if there is any money pump measure that you're thinking about that could be used in this type of models. That's it.
Right. Thank you so much, Carlos.
But I don't know how constructive is your sufficiency argument, but do you think you can use that to sort of bound differences in beliefs in the non-state dependent case?
Yeah, the proof is not constructed, but unfortunately, there is a linear program at some point, and all the solutions to a linear program are give you the rationalizing utilities and beliefs. So it's finite many data. There's no hope of uniqueness or anything like that. But in principle, yeah, computationally you could calculate all the rationalizing probabilities.
Thank you so much, Federico. Awesome. Thanks, Carlos.